Good morning again and welcome back everyone. Let's continue with Professor Sintes' course today. I think we'll get to learn about neutron stars and the interiors.
Thank you. So basically I'm going to continue from where I stopped yesterday. And it's basically, in our case, what we are having is going to be a signal that is almost monochromatic. So it's a continuous gravitational wave signal. In the case of an almost monochromatic signal, basically this is going to allow us to extract narrow bands from the data and to assume, in most of the cases, that the noise, the power spectral density and the band of interest is basically white. So that can simplify a lot the case. Also, in these cases, the signal to noise ratio square, basically, we can approximate a little bit to this integral So basically, you see that the signal to noise ratio square is going to grow with the total observation time. Or, said in different ways, if we will be doing much filtering, the minimum amplitude that we will be able to detect is going to be proportional to the amplitude spectral density and this observation time. If we are doing optimal filtering, much filtering, maybe this number depends on the method to use. This will be this factor in front, 10 to 25 or whatever. Another quantity that I want to talk about is this, so detectable signal amplitude. That more or less we can write like scalings of Sn of f, that is the amplitude spectral density, times 1 over the square root of the observing time times some statistical or geometrical factor. Let's recall the first detection that was done, that was a binary black hole like GW 150914, so at the initial of advanced LIGO, where one was having a spectral amplitude of the order of 10 to the minus 23 hertz minus 1/2. In that case, the duration of that coalescent lasted 0.2 seconds. And here we can put some trials factor of 10. These tell us that the minimum amplitude that we will be able to observe then will be of the order of several times 10 to the minus 22. And actually in that case, the signal was much more stronger because the signal amplitude was very high and the peak was of the order of 10 to the minus 21. If we do this kind of calculations, let's say for a non-pulsar, like the ones that Keith was just mentioning, in which we are going to be able to observe, let's say for observation times of a full year, so if I put here a full year, and also putting this for a non-pulsar similar trials factor, then they tell us, or this gives us, that this is of the order 2 times 10 to the minus 26. So we are able to detect much weaker signals. In practice, this is not true, because in practice, we might just be able to observe signals if they are stronger than 10 to the minus 25, because the trials factor that we will not have to use is going to be much larger. It depends on the search method that we used. So that's one of these calculations to know where we stand. Another quantity that I would like to mention, that I guess maybe also Keith will explain it, is the so-called spin-down limits, spin-down upper limits of the non-pulsars. And basically, this is the assumption, so that the loss of rotational energy basically scales like the moment of inertia, the frequency of the rotation and the frequency derivative, and the energy emitted in gravitational waves somehow is proportional to this quantity here and to this ellipticity. So basically, if we will be assuming that our non-pulsars are like gravastars, that all the energy, that this is not true, is lost into gravitational waves, then if I make these two quantities equal, from the frequency of pp dot frequency and frequency derivatives, I could estimate which is, or I could get an upper limit for this deformation of the ellipticity. So if I do these calculations, the upper limit on this spin down, assuming the spin down upper limit, then gives us that this will be 5, C5, 52, quarter, that's it, minus F gravitational wave dot F gravitational wave to the 5th. And here I have assumed, well, I have already made an assumption this is a triaxial neutron stars and that the gravitational frequency is twice the rotational frequency. If we recalled that the amplitude of the gravitational waves was 4 pi squared g c to the 4. Oops. The distance. So basically, when we know this, we can plug this value in here, and then we can derive the maximum spin down amplitude, that in this case is going to depend on the distance of the source and this quantity here. So this is a number that we take into account, because for sure the amplitude that goes into gravitational waves is going to be much, much smaller than this quantity. But these quantities, for at least for all these non-pulsars, we can compare with the sensitivity of a search for an integration time of whatever we'd like to have. Let's say we can just choose our preferred detector, current or future detectors, let's say for observation time of a year, for a fully coherent integration time, and then we can compare where all these non-pulsars basically live. And the vast majority of them are here, but there are some that are not. So basically, all the ones that are below our sensitivity curve means we have no chance to observe. That is the majority. One should say that there are some of them that are on top of this line, and these are very important. And in particular for CRAP and for Bala, we already suppressed the upper limits a long time ago, already with initial LIGO in the early 2000s. Now, with the results of the third observing run of the LIGO Virgo observatories, already we have 23 pulsars that have already surpassed this spin down limit. Okay, so now let's go back to what was the signal that we are looking for. So the signal at the detector, as I was writing yesterday, is a combination of the two polarizations. It depends on this amplitude. And again, I'm making the same hypothesis that I'm assuming as the emission mechanism that this is a triaxial neutron stars emitting at twice the rotational frequency. Now, this signal is almost monochromatic. It's emitted at almost a fixed frequency. But our detector moves. Our detector moves across the day, across the year. So even at the source, the emitted frequency was basically constant due to the relative motion between the detector and the source. What we are going to have is that the frequency is going to be Doppler modulated. So and this Doppler modulation is going to produce a variation in frequency that depends on the relative velocity of the detector and the source and of the different location of the source in the sky. So this velocity here has two components, has the annual variation and for this annual variation, basically V over C is of the order of 10 to the minus 4. And then there are the daily variations. The daily variations of the rotation. So this is the V of the orbital motion. And this will be the V due to the rotation of the Earth. Of course, things get much more complicated if our source is not isolated, but in a binary system. Because if on top the source is in a binary system, even if it's emitting at a monochromatic signal, we will have to add extra Doppler modulations due to the source being in a binary, due to the motion of the source itself. Okay, also from the other class yesterday, let's say that I do a coherent integration of this signal during a certain time that I call T-coherent. This implies, as we were working yesterday, that I'm going to have a resolution in frequency of the order of 1 over the T-coherent. So if you put some numbers here, if I do a coherent integration, let's say of 1 year, this translates that I'm going to have a frequency resolution of 30 nanohertz. And if I consider a source at 1 kilohertz, you grabbed 10 kilohertz, 1 kilohertz here, then the Doppler modulation is going to be 1 kilohertz, 10 to the minus 4. You will say it's not much, but basically this translates with this frequency resolution that I have 6 million bins in an ordinary Fourier transform. So even if my signal was basically a monochromatic signal, and because if monochromatic, you would say, oh, you could just do a Fourier transform. That's not the case, because for a full observation time, this mirrors along too many frequency bins. So the signal is very simple if the source is isolated. Monochromatic signal, sinusoidal signal, but already we have this first complication due to the Doppler modulation. This is not enough. We have more complications. The next complication is that you also have done the exercises on the F plus and the F cross, the antenna patterns. The antenna patterns, a detector is not equally sensitive to all the same points in the sky. There are locations in the skies at a fixed time that the detector is more sensitive than others. If the source is on top of me, that's the optimal location. If the source is the gentleman in front of me and the arms are like this, basically I'm completely insensitive. So basically, due to the antenna patterns, at a given time, we have some places in the sky in which we are blind. That's not very terrible for us, because we are going to be observing over long observation times. So the Earth is going to move. So if a certain point in the sky we were blind, let's say at a certain time, maybe 10 minutes later or an hour later, we can observe that point. But what we are going to have to deal is with this daily amplitude modulation of the antenna pattern. We also will have to deal with frequency derivatives. And of course, about the orbital motion if the source is in a binary. Not everything is too bad with these kinds of sources that we have to observe for such a long time. I mean, there are also some advantages due to these Doppler modulations. And some of the benefits of having these Doppler modulations is that the Doppler corrections give a precise direction of the source. And another advantage is that a single interferometer or detector can make a detection, a definite detection. So going back to the signal, the signal depends on a number of parameters. So if I go again for this triaxial neutron stars, we were having the zero, the amplitude of the signal. In this model, I'm going to assume that the gravitational wave then is at twice the rotational frequency. Then we have yacht, that is the angle between the neutron star axis and the light of sight. To the detector. So basically, this is the angle that controls linear versus circular polarization. Of the wave. Then we have the polarization, that is the orientation of the bases that are defining the plus and the cross gravitational wave polarization. And an arbitrary phase of the continuous signal at a reference time. This is one first group of parameters, and sometimes the inclination angle and the polarization may be constrained by electromagnetic observations or by using electromagnetic priors. That could be the case, for example, if we have the pulsar inside and using the information of the wind nebula, and in some other cases not. This is the first set of parameters that usually we don't need to search for. So we don't and then there is another set of parameters that will be related to the evolution of the frequency or of the phase, that in principle this will be unknown. And if I make the assumption that I'm looking for continuous waves as not exactly of a newborn, I could assume, so this could be in principle unknown or known, but I could assume that it's slowly varying. And if it's slowly varying, basically, I can Taylor expand, etc. So the first parameters I'm going to have here, as also Keith was mentioned, is going to be the frequencies and the frequency derivatives, the frequencies evolution. The other parameters is the ones that will produce the Doppler modulation. So then our signal at arrival at the detector will not be exactly a sinusoid. And basically this is going to depend on the sky location, so the right ascension, and the declination. And then we can make our problem more complicated if our neutron stars has a companion in a binary. Then here more parameters in which the signal will depend is going to be the orbital period, the projected semi-major axis, if we are talking about a circular orbit, we are going to have one extra parameter. And if we are considering a system with very low eccentricity, then we will have to consider 3 extra parameters. These parameters here, they can be different cases. Either they can be known or they could be unknown. And if they are known, then we can use in the search. And if they are not known, we will have to search for all of them. So there have been a number of algorithms that the different groups and the different parts that are part of the collaborations have been developed depending on what is known or not known regarding the signals. Okay? So basically, so far I've talked about match filtering and that this was the optimal search. So the optimal search method are going to be the coherent methods, in which we can integrate coherently the full observation time. So I'll focus on 2 of these methods, actually the first 2 methods that were developed and used in initial LIGO to search for the first pulsar. So the first examples so I will only describe 2 of the coherent methods. The first one is the so-called F statistics. And in the first class, basically you saw that my signal model that depends on the time, it was depending on some amplitude parameters and some what I was calling Doppler parameters, it was rewritten as a sum of 4 terms in which there were some amplitude parameters that depend on H0, cos iota, polarization and initial phase, and some and then the waves here that depends. So these are the so-called amplitude parameters. And here is what we call the Doppler parameter, so that the one that describes the frequency evolution of the signal. We can also recall that I mentioned that the optimal filter was the likelihood, so the log of the likelihood was rewritten in this way. And now I can rewrite this using this terminology of these amplitude terms described here. So this, the log of the likelihood, given the data and given some amplitude parameters and Doppler parameters, it can be rewritten in a very elegant way or in components. This will be where this x mu of lambda is x, the scalar product with this, and these components are defined in this way: h mu, h mu. So they've just been rewriting the same things in a very elegant way. In the class yesterday, I already made the exercise in a very simple case of maximizing the likelihood for the amplitude of a certain signal. I can repeat the exercise here again, but maximizing over the 4 amplitude parameters. So basically, we can try now to maximize, and this is an exercise for you to do in the tutorial session, that is to maximize the log of the likelihood over the amplitude parameters in order to estimate the maximum likelihood estimators from the data. Basically, what one has to do is to derive this quantity with respect to the amplitude parameters, make it equal to 0, and then from here, one gets that the amplitude parameters are m mu nu x nu, where one has to take into account that m mu alpha, m alpha third is nu. So if you do that and get the A's, and then one substitute them here, then one gets that the optimal statistics now only depend on these Doppler parameters. This can be written in this way: x mu, mu, mu nu, x nu. Or if you prefer more elegantly, you can write like x m minus 1 x. So even if we call it the F statistics, the value of the statistic we refer to is this 2F. So if we do a search using this F statistics, basically the outcome, yes, I erased. Yes? Exactly, these are the Doppler parameters. So these have been the amplitude parameters, and these are the Doppler parameters. It's like that these are the intrinsic and these are the extrinsic parameters. The ones that we have to search for and the ones that we can just get them for free with analytically maximize them. Okay? So basically these are the ones that we have to worry. So basically, if we do a search using these statistics, the outcome of a search is going to be a certain value that this represents the optimal detection statistics for this search. F is going to be a random variable and if we assume that we have Gaussian noise, then this is going to follow a chi-square distribution with 4 degrees of freedom and a non-centrality parameter that is going to be proportional to the amplitude of the signal. In this case, if we will be fixing all the other parameters, we will be fixing cos iota, phi, and phi 0, then we could obtain a power distribution function of 2f for a certain h0 value. And if I do that, I can also try to interpret my upper limits or set upper limits in the frequentist approach. So in the frequentist approach, that will say that the data will contain a signal with amplitude bigger or equal to a certain value with a confidence level C, if in repeated experiments some fraction trials C would yield a value of the detection statistic higher or equal to the observed one. Or translated into a mathematical formula, confidence, we fix the confidence level that we want. Then so if we do a search and we are convinced that we have not seen a thing, for example, and this F star is the maximum value of what we have observed of these statistics, if you want to put an upper limit, what we have to do, a frequentist upper limit, is going to be to derive what is this for, let's say, a fixed value of the amplitude of the signal, and find out which is this value, such as the area of this curve, starting the integral from the threshold or for the maximum value we have observed to infinity, is the desired confidence level of our upper limit. Now you can imagine that to invert this is not trivial, because that means I will have to construct this probability distribution for many possible values of H0 until I would find which is the one that actually this integral matches this value. So initially we are doing hundreds of thousands of injections. Furthermore, our data is not exactly Gaussian, so that it follows a chi-square distribution that's in principle, but in practice, you have to evaluate this basically numerically, doing injections. But this has been one of these approaches. Now I can show you a completely different approach with a Bayesian interpretation. And the other thing is that usually we put population-based upper limits, in which instead of fixing the values of these other parameters, we will be doing injections for all possible values of these parameters. So we will inject huge amounts of populations of signals in order to derive them. I'm going to describe now another method, and this method, this F statistics method, works very well when we operate the data in the frequency domain. And on top, is also very suitable when we want to analyze a huge volume of the parameter space. So this method, I can code it up in a way that I could analyze many different frequency bins and many other parameters for example, in one go. The second method that I want to talk is a time domain method following a Bayesian approach. So the Bayesian time domain search for known pulsars. So basically, this method, I can use it easily, as I say, for known pulsars, when I know the sky position and I know also the spin and the spin derivatives accurately. Basically, the idea of this method is to heterodyne I will explain what this is about. The time domain data using the known spin phase of the pulsar and therefore this means that this requires precise timing from radio or X-ray observatories. There is no problem to include binary systems. In the search, as far as the orbit is known. But that implies that for this method, we have to exclude pulsars if they have significant timing uncertainties. So I've mentioned the word heterodyne. And to heterodyne, basically, it's almost equivalent to multiply the data by A minus I phi of t. So basically I will be multiplying, I will be doing this complex multiplication using the known evolution of the signal. And when I will do that, I will be accounting for both spin down and also the Doppler shift. So after one has done this heterodyning, what is going to be left is going to be a time series that I can rewrite in this way. That is very similar to the expression before. And this vector A are basically these amplitude parameters So basically this is the vector with the signal parameters. And as you can see, after heterodyning, basically the only dependence that is left is these antenna patterns and with these parameters. And then I'm just left with a typical Bayesian problem. Now we will explain a bit slowly this heterodyning, how it's done. Because we don't, or initially how it was done was not to heterodyning in one step, but basically, the how is done, or how was initially done, was to heterodyne the interferometer data at the instantaneous gravitational wave frequency first in a quartz stage, so using a fixed frequency, and with that, we will be able to go to reduce our sampling rate, that if initially was this, we could reduce and downsample the data to 4 samples per second. And then it was a second stage of heterodyning, the fine stage that now was including the Doppler and the spin down, that then would just pass and convert to one sample per minute. This will be my data. So here I can be searching for any pulsar, in principle at any frequency. So my pulsar could be whatever frequency you would like. And for the exercise you were doing yesterday, you will have to use a sampling rate at least twice where there was the maximum content, or you will have to use a sampling rate twice whatever was that you were interested. But if I do this complex heterodynamic, if I know that my signal is around here, more or less all these Doppler shifts and the spin down shifts, meaning that it does F0 and at minus F0, the first thing I can do is this complex heterodynamic to basically shift whatever was here to 0. And then all the data of my interest, all information I want is contained here. Then what I should be doing is to apply a bandpass filter in order to ensure that all the content starting at a certain frequency will be completely 0. And then when I have ensured that, then since all the content will be here, I can reduce my sampling rate a lot. And this is thus the first step. So one passes to has more than 16,000 points per second to just 4 points per second. Now we can even do it better with a second stage that is again to heterodyne using the exact model of the signal, now removing the Doppler and the spin down in order to then convert the signal to exactly at 0 frequency with no remaining modulations. So this was the data, and we have, you see, we have reduced the data a lot because that was reduced to 1 data point every minute. Okay, and when one has this data point at every minute, after, of course, as I said, passing low band passes or low pass filters, what is left is this Bayesian problem. Of course, for each data point, apart from getting the value of the data, one can also estimate the variance in each, let's say, minute of data in order to take into account that they are non-stationaries. And then the Bayesian, well, the other remaining parameters, well, we could get them from the posterior distribution. So basically, the posterior distributions of these remaining unknown parameters, given now the set of points, then I can calculate using the Bayesian theorem. This is going to be proportional to the priors, and the likelihood is going to be proportional to the exponent of minus chi2 divided by 2, where this will be the sum, the data minus the model if I'm interested in computing the posterior probability distribution functions, in particular for H0, if I want to compute this here, given my data, then what I have to do is basically to marginalize over all the other nuisance parameters, cos iota, polarization, and initial phase, given the value of the data that I obtain. So that can be computed. And here, of course, when I've written this expression here, I've been assuming uniform priors. If I have more information, I could use it and I could change those priors. So when we have that, well, we have all the information we are interested in. I can plot what this looks like, and either I have a clear maximum, I might have make a detection and I can estimate the value of the amplitude, or I just get pictures like this, in which this is the distribution A0 given my data values. And there, if I am interested in computing the 95% upper limit, then this is going to be the value such as that the integral gives a 95%. So for example, this would be the upper limit, the one that gives me the area of the 95%. This method also, well, is very easy to apply in principle when you know all the information. And it has an advantage that it can handle very well these non-stationarities in the data, because I'm going to be estimating the noise of the data for every single little piece. And also it can handle very well if we have gaps in the data, because our detectors, the duty cycle is not of 100%, it's mostly like maybe 70%, we have gaps in the data. So now I've talked to you about two methods. But we, as Keith was already mentioned, we have different populations of neutron stars that I can classify depending on the amount of knowledge that I have about the sources. So we have different kinds of neutron star populations. We have the known either radio, X-ray, or gamma ray pulsars. In which the position, the frequency, and the frequency evolution will be known, including the timing noise, including the glitches. We can also have unknown neutron stars. And if they are unknown, means I have no information at all about them. And if nothing is known, That implies I will have to search over all the frequencies, all the frequency positions, and all the sky locations. I can have accreting, let's say neutron stars. Let's say, for example, in low mass X-ray binaries, which the position will be known, and sometimes even the orbit and the frequency. Or another group is known, isolated, but non-pulsating neutron stars, in which the position will be known, but I will be forced to search over the frequencies and the frequency derivatives. Now, I will be able to detect the gravitational wave signal from any of these neutron stars if it's sufficiently lumpy, if it's sufficiently close, and of course, if it's spinning at a rate that will appear in our band. We did not comment on that yet, but yes, Keith did. Basically, our current detectors, let's say, are sensitive between a few hertz, 10, 20 hertz, up to several kilohertz. So from the plot that he showed, there was these blues and those reds. All those reds are below the frequency band in which we are sensitive. So basically, there are several kinds of searches that I can do, but I can either target neutron stars that I can see electromagnetically. That means my searches are going to be in a very reduced parameter space. Therefore, I'm going to have a very good sensitivity that I'm going to explain next. But of course, I just have a very reduced number of known neutron stars with all this information. Since these are going to be my most sensitive searches, maybe I could even discover new things, new physics. I could discover things about the equation of states and so on. Or I can decide to do searches for electromagnetic dark neutron stars. And then I have the advantage that there is a large population, because there are the order of 10 to the 8, 10 to the 9 neutron stars in our galaxy. But our reach, how far away can I reach for this search, is going to be computationally bound. Therefore, I will going to need many different types of search methods to optimize the search, depending what I'm looking for. So, I'm going to talk about methods, and I'm going to divide it just brutally into two types of methods. Coherent methods, like the two ones that I just described, and that means that they require accurate prediction of the signal phase evolution of the signal, but I will be talking some other methods, what we call semi-coherent methods, in which just require accurate prediction of the frequency evolution of the signal. There could also be more other alternative methods that, if I have time, I will also mention, that consider stochastic frequency bundling of the frequency of the signal that can account for other things. Of course, if we know what we are looking for, it's easy to find. And the sensitivity of the searches basically depends what we know about them, and also their computational cost. So I could plot a diagram in which on the x-axis I can put the search computational cost, and in the y-axis you can interpret like the sensitivity, or also the knowledge about the source. So the cheapest and most sensitive searches are the so-called targeted searches. When we are targeting these known pulsars, either using radio, X-ray, or gamma-ray ephemeris. As I said, these will be the ones in which we know the escape position, and I will be doing a search with the phase lock to the electromagnetic signal. That means I'm going to have a very small trials factor. In those cases, the amplitude of the signal scales in this way. I could relax a little bit this to be exactly phase lock to the electromagnetic signal, in case that there is some physics unknown. And for known pulsars, I could do narrow band searches. Again, this is for known pulsars in which I know precisely the sky location, but basically I relax the coupling between the gravitational waves and the electromagnetic wave signal. Basically, I'm going to do a search in a very small frequency band of the order of 10 to the -3, the frequency of the electromagnetic wave. Since there are more trials factor, we have already increased a little bit the cost of the search, and because we are increasing this trials factor, we are not as sensitive as before. Another type of searches we can do are direct searches. So here, what we say, what the information that is known is the sky position, but we have no information about the frequency. Targeted could be supernova remnants. Another target could be the galactic center. Other targets could be the low mass X-ray binaries, like a Scorpio X1. And basically, any search for a neutron stars for which we don't have ephemeris. In this kind of direct searches, I could also include a new class that was also described on Friday last week, that was to search for boson clouds around known black holes. This is also a direct search. In this case, just for a comparison, maybe not with the most modern methods, the minimum amplitude is already getting bigger, meaning the search is worse. Than before. So this factor is growing. And then the most computationally expensive are the blind searches, in which we have no information at all. Unknown sky locations and unknown frequencies or frequency derivatives. So we will have to search for them all. For these kinds of searches, it's completely impossible to do much filtering, to integrate coherently during the full observing time. The only way to do these kinds of service is going to be to employ the semi-coherent searches, in which the total observing time is going to be split into smaller chunks. In this case, the minimum amplitude is going to scale like a certain factor, depending the kind of search we do. And then if my total observing time I've cut it into different pieces of a certain duration, and if I have n segments of them, that's basically that we are going to analyze coherently the different segments, and then with some other statistics, we are going to put together the information that we get. And this is the scaling in this case. Now, of course, if I know what I'm searching for, this is very easy. And as I said at the beginning of the class, for coherent integrations, for a target search, basically the SNR scales like T to the 1/2, T of the observations, T coherent. Now, if I don't know all the parameters, means I will have to repeat the search for all possible values of the parameters. And that's a problem. For example, if I jump to the direct searches in which I know the location in the sky, but for example, I don't know about the frequency. For example, in the case of Cassiopeia A, as Keith was mentioning, that is an isolated X-ray source at the center of a supernova remnant, or also isolated X-ray source. Well, we will have to search for all possible values of the parameters. I'm not going to search for all possible values of all the parameters. How we will set? We will have to set a grid. A proper way to set a grid is going to be to study the metric of the parameter space, set up a certain mismatch, and according to that mismatch, set the grid in the parameters. You can do that very well, or you can have some educated guesses of how many points you are going to have in parameter space. For example, if I want to avoid a cumulative mismatch greater of, let's say, 0.45 radians for a full observing time, because otherwise there will be too much mismatch in phase that I will lose it. That means that my frequency resolution, well, that is fixed by the coherent integration time. The grid in the first frequency derivatives is going to scale like 2 times t coherent squared. The grid in second derivative will be like 6 t coherent to the cube, etc. So, as you can see, it depends how many derivatives you have to include, how fine this grid will have to be to cover a certain range. Basically, if we do a search using a long T-coherent to require to include multiples steps in the second derivative, then the computational cost is going to scale like the T-coherent to the 7th power. So the cost of this search, as you see, rises rapidly for long T-coherent. And depending if the object is young or old, you will have to include more or less frequency derivatives. So in the case, for example, of Casey, this basically limits that one can only integrate coherently of the order of 10 days or a bit more, but not much more. And Casey is a 300 years old pulsar. Now, this was when we know different sky, the sky location precisely. If now I have to introduce the Doppler shifts, I have a number of complications. Because if I don't know the sky location, I will have to also to integrate for many possible locations in the sky. Regarding coherent methods, as I said, I can use this one that I just described, time domain Bayesian search. I could use DF statistics. Well, if my coherent integration time is very, very, very short, minutes, hours. I could just simply do the power Fourier transform. This is longer. Apart from the FS statistics, there is another method developed by a group in Rome that is called the 5-vector method, that basically it assumes that all the phase parameters are accounted for, and this Earth rotation is going to split the continuous wave signal into 5 harmonics, and then is to sum these 5 harmonics. So basically this is a variation of the FS statistics, and I will not describe it here. So for those interested, just go to the references of the literature that I gave you, and then you will find plenty of references of these methods that have been used. If I want to do an all-sky search, let me put you some numbers. Because for blind searches, completely blind searches, let's say that I would like to integrate for 1 year of data. That means, and if I want to do an all-sky survey, so I want to search for all possible values of alpha and delta. Let's say for a frequency range between 50 and 1,000 hertz, only to include first spin down in a reasonable search, minus 10 to the 8 and 0 hertz per second. And let's say that the source is isolated, because otherwise you have to introduce 3 more parameters if it's circular, if not, it gets worse. Well, we have that the number of scale locations scales like the frequency square times a coherent square. And the full computing scales as the coherent to the 6th power without including any second derivative. So that means if I want to do coherent integrations, that would imply that I will have 9.9 trillion choices for sky position, 40 billion choices of F0, 2.3 million choices of F1. So I would have the 920 octillion values, let's say, of the FS statistics to be computing. Now, to compute the likelihood or an F statistics, it takes of the order of 110 microseconds per template, just for one choice of the parameter data. So that basically tells me that I would need a total search time of the order of 2.3 quintillion years basically 5 billions computers running non-stop for about 5 billion years. So you can imagine that I don't have enough computing power to do coherent integrations, to do what I like to work on, that is all sky searches. So I've run out of my time, so I stop here, and then I will continue then tomorrow describing semi-coherent searches. If there are questions?
You said that it's due to the GW frequency not being exactly locked to the EM frequency. So what could be the physical reason for that?
Well, with the different kinds of mechanisms that, that we know have chance to emit gravitational waves, if I consider these three axial neutron stars, then it tells me that the frequency at which has to emit has to be exactly at twice the rotational frequency. There are some other mechanisms that is going to tell me that is going to emit at rotational frequencies and twice the rotational frequencies. If it's due to arc modes, then I know it's going to be more or less at 4/3 the rotational frequency, but not exactly at 4/3 the rotational frequencies. If there is precession, then there is going to be the frequency, the rotational frequency, plus minus this precession. But there could be also some kind of unknowns, and I could consider other things, in which then I let then some freedom, or because I don't trust completely the ephemeris. Maybe, I mean, all these ephemeris data, they will have some errors. So if I don't completely trust them, then what I can do is like, okay, I know more or less what are the values of these parameters, but I just left some freedom to account for my unknowns or to discover new physics. I'm talking basically in these narrow band searches, what is going to be done is going to be coherent searches. The 4-1, in the 4-1, the completely blind, then either we use semi-coherent methods or whatever one comes and invents.